Good afternoon, and apologies for the change in time. I just had a meeting this morning that I had to do, so I delayed this. I didn't want to cancel it completely because I wanted to make sure that we were done with this topic for the week. So I'm going to wait like one more minute just for people to have a chance to come in, and then we'll get started. Okay, so previously we covered in this topic what a force was. So this is just a recap now for our knowledge. And remember, a force is a push or a pull, and the unit of measurement, the way we measured forces, is we measure them in newtons, also shortened to N. So sometimes, though, this force, when it pushes or pulls on something, instead of causing an object to just move back and forth depending on whether, the direction of the force, it can sometimes cause an object to turn. And the conditions for an object to turn, we're going to go through that in a bit, but it happens because there's usually a fixed point where the object can't move. We call that like a pivot. And so when you apply a force on this object, it can't really move from a particular point. It causes a turning effect. So that turning effect is known as a moment. So different from, what we usually say when we say the word moment in everyday language, we usually say, oh, one moment or moment in time. But in physics, moments mean completely different, completely unrelated to what we usually say as moments. The moment is basically the effect of a force that causes an object to turn. And if there is a fixed point, also known as a pivot, that is what is needed for a moment. Because if you imagine, like, say, if you imagine a door that is not fixed at hinges, so there's a door, and we were to pull on this door, well, the door would just move forward then. The entire thing would move forward. Same as if we pushed it back, the entire door would move back. But because it's fixed at the hinges, and in this case the hinges are the pivot points, the door starts turning inwards or outwards. So for there to be a turning effect for a force, there needs to be a pivot. There needs to be a fixed point at which the object can't move at that particular spot, so it turns around that spot instead. And this turning effect is called the moment. So the moment, one common mistake a lot of students make is they would think that a moment is a type of force, but it's not. It's not a type of force, it's the effect that a force has. Okay. And we have a new unit of measurement, and this unit of measurement will make sense in a bit once we look at the formula to calculate a moment. It's in Newton meters, or shortened to NM. This will all be up on the website, by the way, if you haven't already checked. So don't worry about needing to copy this down. It'll be up on the website for you, all of these notes. So this is the formula we use to calculate moments. It is like a simple and straightforward formula. You just have to know what the letters mean. M equals F times D. So the M in this instance stands for moment, and we measure it in Newton meters. And it's equal to the force times distance from pivot. So as an example, let's go back to the door. I'm going to draw the door a little bit better this time. Here's the pivot, here are the hinges, and here's my door handle. Right, imagine yourself opening this door now. You're putting your hand on the door handle. There's you. There's you applying your force to the door handle by turning it and then opening it up. So you're applying a force. If this door handle was super, super close, like by here instead, the distance from the pivot would be super short. Let's say that's like only, I don't know, 0.5 meters or something like that. Your turning effect then on this door would not be big at all. Let's say that we had you applying the same amount of force on this door, but instead the door handle is close to the pivot, whereas with this second door handle here, it's far away from the pivot. The moment of this door handle then would be super, super low, whereas the moment of this door handle would be a lot higher. And the reason why is because of the increased distance from the pivot. So there's two things that influence how much you have with a moment, how big the moment is. It's the force, obviously, how much force you apply, and also how far away are you applying that force? How far away is that from that pivot point? One test that I would normally do in the classroom, you can test it as well at home, but careful, don't break anything or smash anything. You might end up upsetting whoever's at home. So, one thing that I would normally do in a classroom is have a door battle, basically. Have the door open, and you need two people for this. Have one person put their hands close-ish to the hinge of the door. Careful not to get your hand caught in the, in that gap between in where the hinge is. So close to the hinges. And have someone put their hands on the far end of the door on the opposite side to the hinges, so far away from the hinges. So one person is close to the hinge, one person is far away. And then both of you guys push the door to try to get it from one way to the other, and then see who wins. The person who wins will pretty much nearly always be the person who's put their hands furthest away from the hinges because it's furthest away from the pivot. So their overall moment is going to be far larger because even if their force is small, their distance from the pivot is going to be large. So let's do an example calculation using the FIFA method. A force of 50 newtons is exerted on a claw hammer of length 0.30 meters. Calculate the moment of the force. So once again, FIFA method, the first thing you should do is make a list, extract all the information that you can from the question, so that way you don't have to go back and read the block of text anymore. You've just extracted all the information and then move on. So a force of 50 newtons, force equals 50 newtons, is exerted on a claw hammer of length 0.30 meters. So distance from pivot equals 0.30 meters. Calculate the moment of the force. Moment equals question mark. I'm going to draw a diagram of this just so then you guys can see what I mean by moments. Okay. So let's pretend that we were... okay, I'm going to see how good I am with this. Okay, so my nail is here. Oh gosh, a hammer is going to be hard to draw. I'm going to do the best I can though. I'm just going to draw it like that. Oof. There you go. And then there's you holding it. So let's pretend that you are, you have the hammer onto the nail and you're trying to like loosen the nail up from wherever it is. So you are applying a force upwards here. The point that isn't moving is the pivot. The point that is causing the actual object to turn. So our pivot point is going to be here. So our distance is the distance from the force and the pivot in this case. So if you imagine you put your hand a lot closer to where the actual claw is, that's going to make it harder to pull the nail up than it is if you put your hand on the far edge furthest away. Once again, because your distance becomes larger. That's a key point I want you guys to understand, in that the turning effect is a combination of the force and the distance from the pivot. So FIFA method, back to it. Moment equals force times distance from pivot. Moment is equal to, we'll substitute things in. I'm looking at my list. I'm inserting my values. The force I have is 50. The distance I have is 0.30. So I am not going to do this in my head. I'm just going to put it in a calculator. 50 times 0.30 is equal to 15 Newton meters. Now hopefully then this unit makes a bit more sense, because the moment is force, which is in newtons, times by distance, which is in meters. You just end up with a combination then. Newton meters is the unit of measurement for a moment. So just as a quick sort of summary recap of what that means, okay, of what we've just done, is moment is a turning effect of the force. And it's a combination of how big the force is that you're using to turn an object, and also how far away your force is from that pivot point. And the further away you are from that pivot point, the bigger your turning effect is going to be. The shorter the distance from the turning point, the smaller your turning effect is going to be. So think about like everyday objects, guys. We design a lot of tools based on this principle. And I'm using examples such as a door, a claw hammer. But all of these objects is a basic principle of the further you are from the pivot, the bigger turning effect. And we use this a lot in everyday life. Like I said, the example of the door, there's a reason why door handles are on the opposite ends to where the actual hinge is, and not by here, for example. There's a reason why nobody designs doors like that, because it's going to be really, really hard to pull a door open or push it closed if you are super close to the pivot point. Okay, so what this means then, what this moment and what all this moment and turning effect of force stuff means. So we apply these principles, and human beings have been applying these principle of moments without ever defining it for ages. Like we found evidence of human beings making and using levers all the way back in the Stone Age because they worked it out. One thing that I want you guys to sort of be comfortable with is that with moments and the principle of moments, it's almost like intrinsic. It's almost like something that we understand at our core, that the further away we are from a pivot point, the easier it is. So let's take, for example, we were cavemen we wanted to, or not cavemen, we were people back in the Stone Age, and we wanted to lift a rock. There's our rock. I'll label it rock. And then here we are. We wanted to lift this big heavy rock that we can't actually, lift without some sort of tool to help us lift it. So what we did instead is we invented levers. And levers use the principle of moments, uses moments in order to lift heavy objects. And there's a few key points that I want you to know. Is think about where the pivot is, guys. It's a point that's fixed and unmoving as the object turns. In this case, this would be the pivot. The load is the whatever you want lifting. And the effort is basically the force that you're applying in order to cause something to turn. So our goal here is to lift this rock. Well, if we were standing super close to the pivot, our turning effect would be super small, so it would be useless then. So instead, we have this lever where we're stood at the far end. Our distance to pivot, oops, I shouldn't do that. Our distance to pivot is as maximized as possible. So that way, when we have our force, which is effort, times our distance to the pivot, we have a really, really big moment then. And that big moment is a big turning effect on this lever that can then possibly lift the rock up. So we were able to work this out all the way back to when human beings first started using tools. And all of this is based off of moments. And we call this basically a force multiplier because even though we're putting in, comparatively to the actual weight of the rock, a lesser force, by increasing the distance that we apply that force on, we use a small force to lift a large force, to lift something bigger. Because we're increasing that distance, and by increasing that distance, we have increased our turning effect. Okay, here's another example because on exams, they often use a lot of examples, so I want to practice as many examples as you can, just so then you can see that it's pretty much the same exact principles across all these examples. Let's say we were lifting up a safe. In this case, the safe is what we're trying to lift, so it is known as the load. The effort is the actual force that we're putting in. The pivot is the point that's not moving. It might be a little bit tricky to find the pivot at times, but you'll get the hang of it after a while. And so once again, if we put our hands at this point in the crowbar, we probably wouldn't be able to lift the safe. But because we try to maximize the distance, we're maximizing our moment, our turning effect, and then we're able to lift something. So this is another case of us multiplying our force. Another example, bottle opener. So you see the pivot point is here because that's the bit that doesn't, like when we turn this bottle opener, that's the fixed point that doesn't move. We have our small force applied here that's furthest away from the pivot as possible, and that causes a large force on the bottle top. So it's a force multiplier in this case. Okay, now moving on to the principle of moments. Let's say in this scenario, let's say that we had more than one moment going on, right? Let's say that we had a pivot, such as a seesaw, in the middle by here, and we had one turning effect on one side, and then a turning effect on the opposite side. So let's say that we were on the seesaw. This boy here causes a turning effect because he has a force that is pushing down around a pivot point. This girl also has a force that is pushing around a pivot point, so they both have a moment. They both have a turning effect on the seesaw. However, we can balance those turning effects out so then that seesaw doesn't actually move. And this is known as the principle of moments, where if we have two turning effects that are opposite to each other, if they are both equal, then we see a balance out. So the seesaw would be unmoving. So they just be both sat here, not going up or down or anything like that. And so I have here at the bottom total anti-clockwise moments equals total clockwise moments. Basically, we're saying that if the moments on one side is it equal to the moments on the other side, then that way there wouldn't be a turn. So let's look at these numbers. So let's calculate this boy's moment here. He has a clockwise moment because he's moving in the clockwise direction. His moment is force times distance, so 500 times 1.5, and that is going to be 750. So he has a moment of 750 Newton meters going clockwise. This girl, she has a force of 375, is 2 meters away from the pivot. So she has an overall moment of 375 times 2, which is also 750 Newton meters, going anti-clockwise. And because they're opposites, because they're the same number but just in opposite directions to each other, they're balanced out. So there's a complete balancing at that point. Now, I would have shown you this at some point in school if you're in 8Y1. And I remember doing this with you guys because I wanted you to understand that with moments, you can work it out without actually, needing to sit in a lesson about moments, because it is something that is inbuilt. So I'm not going to go over this exactly, but I'm going to put it I've put it up on the website in case any of you guys wanted to have a go again. But in these puzzles, everything is balanced out. Think about where the pivot is. These are all moments. This is the pivot, this is the pivot, this is the pivot. So the further away something is from the pivot, combined with how much it weighs, is going to be its total moment, so its total turning effect around this pivot. And that applies for everything else. So when it comes to what the turning effect of something is, it also depends on its distance away from the pivot. Okay, now we're going to do another example. I'm going to draw it out as well. Dawn sits on a seesaw 2.5 meters away from the pivot. So I'm going to draw Dawn. Actually, we'll draw Dawn. I'll write D on here. She's 2.5 meters away from the pivot. 2.5 meters. Jasmine balances the seesaw by sitting 2 meters on the other side of the pivot. So I'm going to draw Jasmine. I'm going to write J for Jasmine, and she's 2 meters away from the pivot. Who is lighter, Dawn or Jasmine? Now I don't have to do any calculations for this particular question. It's asking me who's lighter. And the question also told me that they're balanced. So that means that Dawn's turning effect is going to be exactly equal to Jasmine's turning effect. Now notice that Dawn's a little bit further away, but she's still balanced with Jasmine. So think about moments. Moments equals force times distance. Now, their moment is going to be exactly the same. Their distance is a little bit different. So who is going to be lighter? Who's going to weigh a lot less in order for them to have the exact same moment? I'll let you have a little think about that before I tell you the answer. If you thought that Dawn would be the lighter one, then you are correct. Because Dawn is further away. If she was the same weight as Jasmine, let's think about this. If she was the same weight as Jasmine, then Dawn would have a greater turning effect. If she was heavier than, then Dawn would have a greater turning effect because her distance is higher. If Dawn was heavier than Jasmine, she would still have a greater turning effect because her distance and her force is going to be higher. So the only instance in which they would be balanced out is if Dawn was lighter than Jasmine, because Dawn has a bigger distance, Jasmine has a smaller distance, so Dawn must have a smaller force and Jasmine have a larger force. So the answer to this is Dawn. She has to be the lighter one. Now let's move on to B. Jasmine weighs 425. So I'm going to say 425 newtons here. What is Dawn's weight? So Dawn, we don't know. This is all puzzle solving, guys. Think about it that way. So notice that I have the distance from the pivot for Jasmine as well as the force that Jasmine's outputting. So what that means is I can actually figure out and calculate Jasmine's moment. Now remember, moment is just force times distance. So Jasmine's moment is equal to force times distance. And that is going to be 850 Newton meters. And because they're balanced, remember, when things are balanced, the moments on that are going clockwise are going to be the same as the moments going anti-clockwise. So that means Dawn's moment also has to equal to 850 Newton meters. Now we just need to work out how much she weighs. So remember the formula, moment equals force times distance. Dawn's moment, 850, is equal to her force, which we don't know, times the distance, which we know is 2.5. Now all we do now is just rearrange to solve for her force by dividing both sides by 2.5, because anything you do on one side, you have to do on the other. And force is equal to 850 divided by 2.5, which is 340. So Dawn weighs 340 newtons. Okay. So just to recap what we've done, because this is hard stuff here. I fully get it if any of you are stuck completely. So, key principles that I want you to understand. Let me do it in a different color. The key thing is for you to know that moment is equal to force times distance. That's the first thing. Now, the second thing you need to understand is that when you have like two moments that are going in the opposite directions to each other, for them to balance out, they have to be equal to each other. So, when you have like an increased distance, you're going to need to have a lower force, and vice versa, right? Because the moment has to be equal. So if somebody goes further away, that means that they need to be weighing less in order to have the same moment. And if you know the moment of one, you also know the moment of the other one if they're balanced, because they have to be exactly the same. So in this case, we knew Jasmine's moment because we were given her weight from the question. We were given her distance from the question. So we were able to calculate her moment. And then we also knew that Dawn had to have the exact same moment. And then we just solved for what we didn't know about Dawn then by using that principle of moments, by knowing that she had to have the exact same moment. Okay. I'm going to skip C just because of time. Let's try this one. A model seesaw is used and a student tried to balance it with blocks. If she placed the first block 0.25 meters from the pivot and the second block weighing 4 newtons 0.22 meters away from the pivot, what is the weight of the first block? So, block number 1 was 0.25 meters away from the pivot. Block number 2, 0.2 meters away from the pivot. And block number 2, we're told, weighs 4 newtons. And we're not told what is the weight of block number 1. Let's try to work this out then. Let's look at the side where I am given all of my information and I'm able to calculate the moment now. So on my right-hand side, if you notice that I'm told the force and I'm also told the distance. So I can calculate the moment of block number 2 by doing moment equals force times distance. So the moment of block number 2 is equal to 4 newtons times the distance, which is 0.2 meters. And that would be 4 times 0.2 is 0.8. 0.8 Newton meters. So the moment of block number 2 is 0.8 Newton meters. What that means is that the moment of block number 1, drum roll, also has to be 0.8 Newton meters because they are balanced out. So the moment of block number 1 also has to be 0.8 because they're balanced and they're opposites to each other on opposite ends, trying to turn the pivot trying to turn the seesaw in opposite directions. They're both going to be 0.8 Newton meters in order for it to balance. Now, what I'm missing is the weight. So I'm going to substitute things into my formula and rearrange for my unknown. So moment is, I know it's 0.8 because it had to have been the same as the other one. My force is, I don't know, so I'm going to leave it as F. My distance is 0.25. Now all I'm doing is rearranging for F by doing the opposite, which is divide because it's times on, and I do the same on both sides, and I'm left with F equals 0.8 divided by 0.25, which is 3.2 newtons. Those had cancelled. And that is my final answer. The weight of the first block had to have been 3.2 newtons if they were going to balance out. Okay, so I know this is difficult stuff, but I want you guys to get to grips with the idea of moments being turning effective forces, and that the bigger the distance or the bigger the force, the bigger the moment's going to be. And in order for two moments to balance each other out, they have to be exactly the same. And then you can use that to be able to calculate for any unknown weights or any unknown distances. So if you have a look at the website, I have on the website a little bit of practice. I'll link directly though. There we go. A little bit of practice. On the left-hand side is the sheet. So with the first couple questions, it's mainly just asking you guys to understand and be able to know where the pivot, where the load is, etc., etc. Question number 2 asks about using your knowledge of maybe why for embroidery scissors, we use like scissors that have like a really, really short distance from the pivot point of the scissors. We'll think about the turning it with embroidery scissors, what you want to do, how much of a turning effect you actually want. Question number 4 onwards, so question 4 is basically doing a bit of calculations, but it's just one set of calculations of force times distance. And then question number 5 is the challenge, basically, where you want to figure out the unknown based off of your knowledge of the principle of moments needing to balance each other out. So have a go at that. Also, the second thing on the PowerPoint, at the very end of the PowerPoint, I have the answers there for you for that sheet. So I know that with moments it is a bit of a struggle, but don't worry about it. When we get to year 9 and further on, you guys will recap moments again. So if you found it hard in year 8, don't stress out too much about it. It is mainly just supplying you with a little bit of background knowledge so you feel a bit more confident going into GCSEs then when you have to do a bit more practice on the calculations. But my key point is I just want you to understand what a moment is, how force and distance is related to moments, and if you can push yourself to do some calculations, feel free. That's awesome, but at this point, if you're struggling with the calculations, that's fine by me. All right? So I'll leave you to it then. Have a go at the rest of that. Have a go at that sheet, and the answers are there for you. All right.